Good morning and welcome to this presentation of this paper on the prevalence of code smells in machine learning projects, as written by me, Bart van Oort, my supervisors Luís Cruz and Maurício Aniche, and overseeing Professor Arie van Deursen. First, a little bit about me. My name is Bart van Oort. I'm 25 years old. I'm a software engineer by profession and by heart, and I'm currently doing a master thesis at the TU Delft on the code quality of machine learning applications. And I'm doing this in collaboration with the AI for FinTech Research Lab from ING. This is a 5-year collaboration between ING, the global Dutch bank, and TU Delft. And we have researchers, PhDs, postdocs, master students in all areas of AI, and also in data analytics, software analytics, and all in the context of financial technology. Now, I'll first be giving you a little bit of an introduction on this paper. I'll talk you through the methodology that we used, the results that we received, the implications that we found for practitioners and researchers, the threats to validity, and finally some closing remarks. So let's get into it. We did an empirical study on the prevalence of code smells in 74 machine learning projects as written in Python. It's important to define what code smells really are. So we define code smells as potential defects in the code, refactoring opportunities, and coding standard violations. And these code smells have been shown in research to affect several aspects, namely maintainability primarily, but also understandability and complexity of the code, so how easy it is to read through the code and still understand it. But as we show, it will also affects reproducibility. Now, we did this study in order to get some more insight into how many code smells exist in machine learning projects. And to that end, our research question is as follows: what are the most prevalent code smells in machine learning code? Now, to answer this question, our methodology consists of 3 stages. These stages are project selection, setting up the code bases, and static analysis. So, starting with the first one, project selection, we had several selection criteria for the projects that we employed. First of all, they have to be hosted in a Git repository and they have to be open source. They have to also be written in Python 3, because Pylint only supports analyzing Python 3 projects. They have to contain pure Python code, also because Pylint mainly supports directly analyzing pure Python code. They have to be applications of machine learning and AI. And now, why is that? Specifically, we are not interested in analyzing libraries for machine learning or AI. We are rather interested in analyzing applications of which the primary functionality is fulfilled with machine learning or AI techniques. Finally, we wanted the projects to be deliverable. And now this is quite a fuzzy definition, of course. So we tried to define this as having been submitted to a Kaggle competition, paperswithcode.com or reproducedpapers.org. And the idea of this selection criterion is to filter out any toy projects or unfinished projects. Now, next step is setting up the code bases, and that basically consists of performing a git clone and installing the project's dependencies. And you might ask, why would we do this? Well, there's a couple of rules in Pylint that check whether libraries are properly being used. And that's specifically important for machine learning, as Scully et al. In their 2015 paper also found that machine learning code has a high degree of being glue code. It tends to glue together the functionalities of several libraries, and thus it is important to see whether these are indeed used correctly. Also, a similar study to ours by Simmons et al. Found that it was impractical to reliably determine and install dependencies for the projects analyzed, I quote. But if it's so impractical and difficult to reliably determine and install projects' dependencies, then that is in itself an obstruction to the reproducibility and maintainability of these projects. And hence, we also think that it should be included in this study. And spoiler alert, this was not very trivial, but more about that later. Next step, static analysis. In this step, we simply run Pylint in its default configuration, and we collect and count all the messages that it reports. Now, applying this methodology, we got 74 machine learning projects totaling 131 gigabytes, including their Git history and the virtual enums containing all their dependencies, and resulted in a top 20 of all code smells per category. Now onto the results. This is a distribution of the Pylint messages that we received, and Pylint reports its messages in several categories depending on the severity of the issues. And using the median as a main measure of central tendency, we noticed that there are particularly many messages in the convention and warning categories. But more interestingly, the median project also had 56 error messages. And error messages are actually meant for probable bugs, things that are very likely to actually be a bug. And even more interesting, we found that no project had no errors. Every project had at least one error. Now, looking at these code smells and their counts in more detail, we found a large number of invalid name messages. So these are classes or functions or variables that were not named according to the PEP8 naming convention. We found also a lot of duplicate code messages. There were also a large amount of classes and functions that had too many arguments or too many statements, too many local variables, generally too complex functions or classes. We also found that import management in the warning category, there are lots of messages about import management. Unused wildcard imports is the most reported one. And in the error category, we also found a lot of problems relating to import management, specifically import errors, but also no member errors, which are also related, and undefined variable errors, which were caused by imports that did not resolve. Now, this is a nice big table, but what does this really mean for practitioners and researchers? So, going on to the implications, we found that code duplication is very common in machine learning projects. We found a number of projects that were copy-pasting experiments. So they had one big script where they performed an experiment and copy-pasted that a couple of times, and made some small changes to them to just try different variations of a specific experiment. This copy-pasting of experimenting kind of aligns with Scully et al.'s observation of experimental code paths remaining in the repository or in the code. Next, we found that PEP8 may not be necessarily applicable to machine learning. And Simmons et al. Also conjecture that this might be because machine learning is inherently quite mathematical. So it makes sense then that the code for machine learning also has this resemblance to mathematical notation. And finally, we found that Pylint fails to reliably check import statements. This goes for both a local import, so importing from a file in the same project, as well as importing libraries that are backed by a C implementation. And specifically, PyTorch was one of the biggest ones here. Now, coming back to installing those dependencies, we found that there is bad dependency management in these Python machine learning projects, as 32 out of 74 projects had an invalid requirements file, i.e. the dependencies could not be installed without any changes to the project's repository or files within the project's repository. Now, a large part of these invalid requirements files were requirements.txt files that were generated with pip freeze. To clarify, pip freeze finds all libraries that are installed in your current Python environment. And generally this is then piped directly into a requirements.txt file. But this pip freeze command also includes any indirect dependencies, any dependencies installed from God knows where, but not PyPy, perhaps, and also dependencies that may be used for other projects you installed for other projects, but are not necessarily being used in this project per se. This is especially bad when not using a virtual environment. So pip freeze creates these requirements.txt files that are difficult to maintain. With all of these indirect dependencies, it's very difficult to still find which ones can be updated and which one cannot be updated. There's a potential to also include unresolvable dependencies, those dependencies from other package repositories than PyPy. And it has the potential to include unrelated dependencies. We even found some projects that included, YouTube downloader, even though they did not do anything with video analysis, or even OS level Python dependencies such as Python apt and app armor. Now, these bad dependency management practices pose a major threat to the reproducibility and maintainability of machine learning projects. And they are also an extra obstacle towards the adoption of CI for machine learning projects. Now, our research is obviously not perfect. We realize that. And regarding the validity of our data set, we only used open source projects. But in order to be more representative of the real world state of machine learning projects, this data set should either be expanded to also include closed source projects from industry partners. But we could also compare the results from open source projects to industry projects and see how they compare. Are there more or code smells more or less prevalent in open source projects than in industry projects, or vice versa? Furthermore, we also did not analyze Jupyter notebooks. As I said earlier, we only analyzed pure Python files instead of Jupyter notebooks. And while it is possible to extract Python code from Jupyter notebooks, there are a couple of pilot rules that would not make sense on code that is extracted from Jupyter notebooks. And we did not want to use two different measuring sticks for the same project. Now, another issue is the validity of PyLint itself. Linting in Python is notoriously difficult, mainly because of the untyped nature of Python. And PyLint also has a number of bugs that either cause it to produce false positives or false negatives, as we have also seen regarding these import errors. And we hope that this sheds some light on the prevalence of code smells in machine learning projects, as well as making us more aware of project level smells in machine learning projects, such as bad dependency management. Thank you for listening, and I wish you all a good day.
Hi, and welcome backstage. Now, we thank you very much for the questions in the chat. So first, there are questions related to how you selected and defined the projects you studied. Can you briefly summarize that?
Yes. So we had these selection criteria, and I saw a question specifically about the deliverable section criteria. The idea was that we had the projects that would be at least capable of almost being run in production, or having some form of seriousness to them. And yes, we did discard some projects that initially we did discard some projects that we thought were not deliverable, that we thought were just too toyish to really work with.
Right. And with regards to machine learning techniques, is it all over the place, or there are some specific techniques more applicable?
So what do you mean exactly?
Among the projects, so are they machine learning, deep learning? Are there specific libraries that are more commonly used?
Well, we specifically opted to go for applications that just use some form of machine learning. So which an application of which the core functionality is fulfilled using a machine learning algorithm. And we don't discern in whether it's a supervised algorithm or an unsupervised algorithm or a specific type of machine learning. What we did want is we wanted the projects to be applications of machine learning. So we really wanted them to be like a trainable, testable artifact, instead of something like a software library that is used within these machine learning projects.
Okay. So now the clarification question came that large number of projects come from a competition and other sources which are not directly projects being used for real users. Is that correct?
Yeah, so indeed, a very large number, of these projects, they did come from Kaggle competitions, and also from reproducepapers.org, as well as from industry players such as NVIDIA and Google's DeepMind. And it could be a selection bias as well. To be honest with that, it could be a selection bias too. But if you have any good projects that might fit, or that might be really useful to include in this study, then please share them. I'll be able to add them even.
When in your study, can you the issues you have found, are there any indication of lack of knowledge? So that's they basically don't know what is a good software engineering practice and don't apply it, or is it lack of ambition? It's more, I mean, exploratory, and that's why they don't care very much. Do you think?
I think it might be a combination of both. It can be indeed that the idea is that it's very exploratory and that it doesn't really matter too much whether you have capable dependency management or you have all linting set up. That might not be a very big concern, but it may also be because they're maybe not aware of how what the advantage of it can be. I've noticed it myself, and probably some people here in the audience, lots of people here in the audience as well, that while you're programming something and you have all of these linters set up and type checking statically, and I don't know what kind of other software engineering magic that's going on basically while you're programming. It's really great to have that. It kind of is a falling net basically sometimes. And maybe the data scientists that usually create these machine learning projects, that they're not used to this, and then they don't know what they're missing even. So I guess it is also indeed an education thing to make sure that the data scientists also know of the kind of software engineering tools that are available
Right.
for developing quality machine learning projects.
Great. Thank you very much for this short chat. And now in a few seconds, the next presentation will start.
Yes.